Cool. All right, everyone. So let's get started. Thank you, everyone, for showing up. Um, yeah, this the title of this talk is Gaia Network for planetary-scale, safe, transformative AI. I know this is a big statement, so I'm going to do my best to back it up. But I'm also going to leave a lot of time afterwards to talk and discuss. So if you have any big questions and or a source of skepticism or whatever, yeah, take note, and I'll make sure to try to cover as much as I can afterwards. Um, so yeah, as I kind of intimated at the pitch session, I'm sneaking in here with something that is not strictly AI safety. It's really everything safety. And the reason for that is that I and the other people that make up the group that's working on this, we really think that the solutions that are needed for AI safety are turn out to be exactly the same that are required to solve like the messy jumble of things that we call the meta crisis, which does include billions of highly capable intelligent agents, whether those are AIs or let's say ill-intentioned corporations. But it also includes all sorts of like multipolar traps and coordination failures, all instantiations of Moloch, whether they're AI related or not. And finally, the kicker, which is that really everything is connected. So all the economical and physical and otherwise ecological and so on impacts of AIs in the world are connected to existing crises like the climate crisis, the food crisis, the ecosystem and biodiversity crisis, the physical security crisis from mass migrations and name your crisis. So our thesis is that if you on one hand, if you put all of these things together, you do get total risk for all of humanity and the biosphere. But at the same time, the solutions, as I said, are you have to get solutions to this. You have to think holistically. So we might as well start with something like AI safety, which as we're going to see is a really good application for this. And so yeah, Daniel Schmachtenberger, who really was a big popularizer of this idea of the meta crisis and in public discourse, has hypothesized that there are two attractors for the meta crisis, two likely end states for this combination of factors. One of them is chaotic breakdown of all the physical, social, economic infrastructure that we a species depend on, and the other one is the Butlerian jihad. It's oppressive authoritarian control in an attempt to try to keep the first outcome from happening. The question is, can we design a third attractor? Can we design a set of interventions, some changes to our existing infrastructure, to our existing capabilities as a species that leads us into a steady state that is win-win, that is stable and avoids those traps that we associated with meta crisis. We believe so, and we believe that the answer is actually a lot of the answer has to do with being able to take what we know works. The transitions here are a little bit junky, but the idea is to take what we know that works, which is this ability to make model-based predictions and decisions and connect them in a decentralized protocol that lets us as a species make sense of a complex world, make better decisions, make better dialogues, make better negotiations. And we're talking about us here. It's really people, AI agents, organizations, everybody. And what does one thing have to do with the other? Well, I'm going to get into details, but the principle is really simple: is that if all these different agents have access to a shared, mutually trustable source of quantitative knowledge and models and predictions, then you can actually bridge a lot of the trust gaps that lead to these multiple traps and other game theoretical undesirable situations that are underpin Moloch, and that unlocks win-win solutions that unlocks a lot of the positive outcomes that we know that we need. And we know this is true because this is like this is what having a knowledge commons does for us, whether that's speech or written language or anything else. And we just want to take that a step further. And specifically, there's a bunch of different applications for this, as I mentioned, but the one that I'm going to be spending most of the time is really talking about safe AI, especially as it pertains to the physical world. And physical can also mean economic. It just means, I'm not talking about social media, I'm not talking about bias, I'm not talking about any of these things. I'm talking about places where agents can have direct direct economic or physical impact on the lives of other agents. So first, what I'm gonna do is I'm gonna describe how Gaia works, and I'm gonna try to go fast here. Then I'm going to spend a little bit more time talking about the application to AI safety. And finally, I'm going to discuss what are the design challenges, what are the interesting things that we have to deal with as we're trying to turn this into the kind of abstract generic description that we have here into a working piece of software, which is something you're going to notice about me. I'm a practitioner at heart. I think theory is nice. I think discussion is nice, but I only care about whether we can actually put things into practice and make them work, and ideally make them work in the timelines that we need to avert or mitigate catastrophe. Otherwise, it doesn't really matter. So back to how Gaia works. It's actually quite simple at a high level. So there's five principles. Four of those we're pretty sure about, and the fifth one we're reasonably confident about. The last one, but we're gonna get into it. So at a high level, users contribute quantitative knowledge claims that come from data and models. We as in the network, it's a decentralized protocol, much like the one that we're using right now, TCP/IP, much like HTTPS, much like all the other protocols that make up the web, some of which use your thinking Web3 crypto technologies. There's uses for that as well, but I want you to think protocol in this more like generic web/internet terms. So it's a protocol that lets nodes score each other's contributions by quality and impact, and that also lets nodes query each other and aggregate answers across each other to answer user queries. The fourth big principle is that the way to disagree with each other in this network is just like you disagree in the web. You publish something that competes with it, but because we are, it's not just a matter of whose voice speaks the loudest, but it's actually a principled way to score contributions. The convergence is not on the loudest or the most popular, but on the best models. So on the best beliefs, the things that match reality the most. And the fifth one, which is probably a little bit more controversial, is this idea that, well, you need to finance this network, you need to generate incentives for knowledge to be produced and contributed. So the way to do this is to monetize queries. So if you're thinking about the examples that I'm going to be giving here, they're coming from the kind of work that we have been doing in the last couple of years, which have a lot to do with climate, nature, sustainability. But hopefully you're going to be able to see, and I'm going to give a more concrete example later on, how this connects to some of the more common types of AI safety contexts that we've been talking about. But just for the sake of the examples, stick with me here. So yeah, when I say that users contribute these beliefs, these contexts, these beliefs that are relevant to a certain context, what I'm talking about is that each node, like each server on the Gaia network, it hosts some data, but this data is not HTML and JavaScript. It's structured data about the world, which can be observational data, or it can be probabilistic models. Models are code, which is data as well. So these things, this data about the world, which we call beliefs, They're really claims about how the world works, about how a specific context works. And a context can be very high level, can be about the whole Earth, like in this example here, about the Earth's climate, or it can be a very fine-grained context about a specific neighborhood, a specific building, a specific microchip, whatever scale that you want to talk about. But yeah, so like in this example here, you can see that you can have beliefs about facts on the ground, like how much carbon gets captured in a farm, effects of interventions. You can have claims about causal structures, which are pieces of equations, which translate to pieces of probabilistic programs on a model, scientific parameters, predicted outcomes. These are all beliefs. And as we talked about, any website can host any content, and the same as any node in the Gaia network can host any beliefs. However, we know that some beliefs are actually more useful than others in reality. So we want the network to ground these beliefs in how much they are appropriate to the world as it exists, according to basic probability theory, aka the logic of science. And the way that we implement this is that nodes score each other on the basis of usefulness, which is measured by this quantity called free energy reduction, which is an approximation to free energy is an approximation to model evidence. I can get into the technicalities of that. And that is only computed where the beliefs are relevant to user queries, essentially. And contributions are rated by trustworthiness, where this also gets associated with cumulative explanatory power compared to alternatives. So how much better a node's beliefs are at explaining the world than others, and this gets accumulated over by contributor and so on. And these scores trickle down the graph as it's exemplified here on the right. So models are attributing value to each other, and these trickle down according to how much you depend on other nodes' beliefs, on other nodes' data and model queries. And this really just kind of provides a way to account for the value of beliefs. That is its compositional, it's transitive, it's actually really an accounting metric. It's really appropriate for these uses. And having that, I'm going to speed up here because I've noticed we're already at 11 minutes. But the way to use this is essentially like Google. You compute. You need a computation, need a query, like for instance, a predictive query about what's the effect of one intervention. As we talked about, the world is connected, so you want to do an intervention here. You want to have evaluate whether it's safe for an agent to use a certain kind of pesticide, or for an agent to go and have some physical behavior somewhere. Maybe it's a factory robot, whatever. Often these actions have effects that ripple across other domains, and the protocol here, it allows you to do to calculate exactly the cumulative effects here. So you can express a question as a query to a certain node, and it queries what's going to happen as a result of this to all the nodes that are in the neighborhood, and that propagates out and then gets aggregated back. And unlike Google, where all of this happens as a MapReduce job within Google's data centers, in the case of the network, this happens as a distributed computation, but the principle is more or less the same. The fourth principle is really clear. Instead of trying to convince people on Twitter that you're right and other people are wrong, if you think there's a better way to model something, or better data that proves that something is unsafe or wrong or whatever, the way to do it, to make that case, is to publish stuff on the network. And finally, we think that a really the only long-term sustainable and value-aligned way to find a separation of this network is to have users put their money where their mouth is. There's a lot of discussion here, so we can talk about that later. But we really believe in this idea of incentivizing users to publish high-quality network in high volumes by monetizing queries, and thus creating what we call a data value chain, or a knowledge economy. About halfway through already. So big question is, will they use it? I'm not going to go through the details here. The first target opportunity that we've been talking about, which is this idea of how can you actually use this kind of distributed computing and an inference system as a way to unlock action and direct research in places like climate science, in places like nature risk mitigation in food value chains, and in places like regeneration project impact forecasting, all of which are super important, and I care about a lot of them, but the one that you're here for is AI safety in real-world systems. The case here that I keep making is that it's already a problem. AI is proliferating, has been proliferating for a bunch of years across all kinds of applications. You may know it as autonomy. You have it in all kinds of machines. These are neural networks. These are other kinds of black box models that get deployed into robots. They get deployed into cars. They get deployed into factories, and they're increasingly left to make decisions, whether intentionally or not, which makes them effectively autonomous agents. And these black box systems, they're very complex and increasingly complex. They're very capable already and increasingly capable. And we all already know that they cannot be adequately supervised by humans today. So this is not a future problem, it's a today problem. And what we have today is mounting risk from these systems, which is a big problem because this is risk that accumulates across a global system that is interconnected. So if you have failures in an AI system that makes decisions about, let's say, about resource allocation in a food company, in a value chain, that is planning for how much to buy seed from place A versus place B. If that gets too greedy and or short-termist and allocates too much resources for one area, and that area fails, bam, you have fragility in the system, which means famine. It's a real world problem with real world consequences. This is what I mean by AI safety today. It's not necessarily AGI causing Skynet type problems, but it's potentially as bad as, because if you have large scale famines that are generated by over optimization, it's already pretty bad. So Joshua Bengio, Shane Legg, Davida, Steve Mohundro, a lot of people have been proposing things that look sort of like safeguarding AI deployments through model-based oracles or gatekeepers. And what we argue is that gatekeepers that use the Gaia network as a source of predictions and evaluations of agent policies can vet and constrain AI agents either in advance by providing pre-validated safety plan type assessments, or at execute time while the agent is operating as true gatekeepers, let's call it. And this scales. This is basically the only thing that scales, we argue, because it's the only approach where you can plug in basically any context and any model and have it be assembled into an evaluation for any kind of combination of context that makes up a system. So let's talk about an example. I was really counting that we're going to have the demo ready. It's still about a week to go, but at this season's SPAR project with a bunch of awesome students and mentees, we've been working on a sample implementation of this, which focuses on calculating and enforcing sustainable fishing practices to safeguard the sustainability of AI fishing vessels. If you've ever read The Mountain in the Sea, it's similar to we're very inspired by that setting, which again, it's a problem that already exists today because fishing vessels are incentivized for the short term to fish however much they need to recoup fixed costs, which causes overfishing, which causes increased fish scarcity, which causes increasing overfishing. So you have a positive feedback loop, a tragedy of the commons. And this is nothing to do necessarily with AI, but in the presence of AI, you have just basically a more more ruthless, more difficult to control situation where these fishing vessels, they can be anywhere in the ocean, they can be doing whatever they want, they can be overfishing to their heart's content or to their AI brain's content, and therefore, as stakeholders, you really want a way to generate constraints to be able to calculate how much is a safe sustainable fishing policy for the whole system, and to generate constraints for each individual agent to do that. So basically, that's what we've been working on, and we're going to have a pretty nice demo of that. And so the description that is pretty general, and really it applies to a lot of other situations. We've been talking about settings, as you're going to see, in autonomous vehicles, in industrial automation, in defense, and all these settings there, they have real world counterparts, where the question really is, how do you calculate transparent, clear, and interpretable, and real-time generatable safeguards that you can evaluate an agent's behavior against. So if you think about scalable oversight, this is it, where it's not just the oversight that is scalable in the sense of what's happening. How can you oversee billions of agents, but also how can you make sense of what's going on with billions of agents, so you know that your safeguards are right in the first place. So this sounds great. I think you'll agree with me that it sounds great, but what's the catch? The catch, as I keep arguing, is that in the real world, there is no proof. So if you're thinking about how does this compare with something like Davidad's plan or Steve Omohundro's proposal, is that you won't hear me talking about proofs, and that is because the map is not the territory. That is because, as for instance, Nicholas Taleb has alerted us to, and a bunch of other people as well, there is this asymmetry between the small world of models, where there is provability, there's the ability to make definitive and absolute statements, and therefore you have some confidence that things are going to be true, and you don't have to worry about context or about pesky details, anything like that. And the real world, where any given model is just an approximation and across dimensions that far surpass our ability at any given time to predict what there's going to be. And the way to understand that difference is really about thinking about a missing layer of randomness, which we call model error, which introduces fragility into any kind of decision-making or safety management procedure. And this is really important. I keep coming back to this because the emphasis, if this is true, then the emphasis on building these systems for safeguarding, it has to be very different. It's not about proving, it's not about providing guarantees. It's, well, I'm not gonna spoil the fun, so you're gonna see what it's about. And as I've been alluding to, there is this idea of, well, if AI safety is really everything safety, then you should actually be able to build systems, frameworks, and processes into our world economy that take everything into account. And we actually think that this is pretty true because, you know, businesses deal with risk in certain ways, and there's some very strong similarities between all these different types of risk and safety analyses that businesses have to deal with every day. So our argument is that by just connecting into those frameworks and enhancing them so that they are Gaia compatible, they're talking the language of probabilistic models, and they're versioned, they're traceable, they're auditable, they're connected to other models, so that we have that we can look at things in the big picture. They are based on models that are generated in an informed way by a wide variety of prior knowledge, so that we know that we're measuring risk against the right things. If you do all of these things, then great, then you have something that is AI safety. So here's what we were talking about here in the industrial context is plant automation or safe autonomy. But it's also AI in the loop. It's also guiding plant operators to make safe decisions. And it's also safety, industrial safety in a more traditional contexts like reporting on how safe are your operations and the product that you're delivering to customers, regulators, and your own internal stakeholders. So, for instance, if you're Boeing, if you guys haven't paying attention, Boeing hasn't done this, and they're paying the price. And my argument is that they could be doing this and getting all the benefits of a principled approach to risk management, and the existence of such a thing as the Gaia network can solve these problems for companies like Boeing in the context of building safe products, or companies like BMW in the context of building safe cars, at the same time that is solving problems for companies like Tesla, who are trying to build safe cars without drivers, right? So it's basically really the same sort of mental framework that I want you guys to have in your minds. Okay, so I've made a lot of big statements, and we have code to back it up at a high level, but there's a lot of really important details, and these are the design challenges that I want to share with you. First one is, well, how do you bootstrap a model network in this huge problem space, which really means modeling everything? As you know, we talk about modeling everything. Davidad, Steve O, everybody who really thinks about this really realizes that at some point you're going to have to cover the entire world, which is exactly like for the web to work, for something like Google to work, you really at some point have to have coverage of the entire world in terms of information. And bootstrapping it, the initial part of building up that library, it takes a long time. And you know, Fred Brooks in his 1995 book about the design of design, he talked about this, right? The hardest part is really assembling a good initial library of starting models. And it's a problem because if you don't have a good model, it's very hard to get adoption. And if you don't have adoption, it's very hard to get the experience that you need to build a good model. However, we are lucky that we now have LLMs that are very good at coding and modeling, and we have a vast backlog, so to speak, of human knowledge expressed either as natural language or formal equations about how things work. Which is in the web. A lot of it is scientific literature. A lot of it is more informal, but we don't have to do it from scratch, right? We can just take all these repositories of knowledge and literally encode them as probabilistic programs. And for the things that are not quite ready yet, we can have stakeholders play around with it interactively until it makes up for the right model. So we did a lot of experiments with this last year. This is a model that we built for agriculture using an LLM. This year, Gideon Segehi published this nice piece on Less Wrong about constructability, which is basically the same idea. And last year, these folks at Joshua Tenenbaum's lab published this paper from word models to world models, which has a variation of the same idea. So we kind of know how to do this one. Another kind of difficult problem is how do we get to good enough credit assignment and a good enough knowledge economy to get the ball rolling. So at a high level, again, we argue that if we have a low enough level of contamination or a good enough ability to ignore contamination, meaning noise, misinformation, and so on, the network's content will converge to be truthful, because that is the property of Bayesian updating. So that if you have access to data about the world, then your models, Bayesian updating will get you posteriors that reflect the world. That's just the logic of science. And to the extent that Gaia has truthful knowledge because of one, it will be economical to continue filtering out or ignoring arbitrarily large amounts of contamination. So you have a closed loop between these two things. And that is because Bayesian updating is generally reversible unless you do something really stupid. And Gaia storage is append only, so it can have unlimited amounts of rollback. So that's great, but in the long run, we're all dead. So to get to good enough in practice, you have to do a lot of work, and that can include building meta-analysis and measurement models into the system so that we know We know what kinds of data and models are good. Trust and network models, so we know what kinds of nodes are likely to have been corrupted and should be ignored. Create liquidity in this knowledge economy and have the incentives right. So that's all of this is pretty hard and I would say a pretty wide open design space. Another big problem is, well, we talked about Gaia as being sort of like a distributed equivalent of Google, but Google really only worked because of PageRank, because it turns out that you could compute relevance of web pages to queries using this very clever, very efficient algorithm. And without something like it, the worst case network load in a strongly coupled system like the real world, it's quadratic in the number of nodes, which sucks. However, we think we can use something like GFlow-nets to amortize inference. I'm running out of time, so I can come back to this, but we believe that this can, using this technique, we can have nodes amortize these costs, and it keeps network compute load at basically a constant level. Finally, as I talked about, there's a big problem of model error, which is essentially that because you're trying to use small world models to represent real world problems, you're always running into some kinds of risks that have to do with choosing the wrong model. In particular, if you're making decisions that are predicated on an assumption that your model has thin-tailed distributions like Gaussians, or basically, and most kinds of distributions that are used in the day-to-day. You can have fat tails disguising as thin tails for more or less forever until they pop up. And when they do pop up, their effect is arbitrarily large. So the classic example is Taleb's turkey. This is the story of a turkey. The turkey's born and he's pretty happy. He thinks he's having a pretty good life. His life is pretty normal. There's nothing more or less, life is more or less the same in the turkey coop every day until Thanksgiving Day. And then the turkey gets a nasty surprise, right? And everything that he thought was true and thought he had learned from the past, his entire world model turned out to be false. And when it was false, it was the only thing that mattered. So again, like the general idea that I alluded to before is that if you are an agent, whether a human or an AI that is aware of this, you can harden your decision against model error instead of naively assuming that your maximum a posteriori model is good enough or can be made good enough with enough data. And turns out that there's a very natural way to implement this called hierarchical active inference, which is basically just using a hierarchical model that is composed of a bunch of different submodels and spreading your evidence across them in a principled way. So you can handle this. It just makes things more expensive and harder, but it's really the only way to do it. And the nice thing about the network is having a network approach is that you can offload that cost of making sure that you have the right model for each context to all of your peers that actually know about the different contexts. Okay, there's a bunch more other stuff that is important that we want to do. More real world use cases. We have some work to do on the infrastructure and complete development of a bunch of things. But in a nutshell, that's it. We've been working with a lot of really awesome people across continents, nationalities, languages, time zones. And if you're interested in this, I invite you to work with us as well to help us build the planetary web of models and create safe everything. Thank you.
Awesome. Thank you so much for the presentation. We have 23 minutes for discussion. We had some questions in the chat.
Okay, I didn't see that.
Yeah.
Pull it up. Okay, one of the questions is, can you share the link to the slides? Yes, I can. I'll do that right now. I think this link should work. If it doesn't, let me know. Okay, so David, first you asked, what is the argument supporting that LLMs are good for quote unquote modeling? Can you define what you mean by this? And then what kind of approximation to Bayesian updating will Gaia do? What algorithms in particular? Okay, great questions. So I'll go to the second one first because it's easier. So instead of trying to fix a particular algorithm for Bayesian updating, we fix requirements, which is consistent with our idea of a protocol. So basically, the requirement is that you have to be able to calculate a free energy for your model. So you can the usual way to do this is to do some kind of variational free energy, sorry, some variational method, some variational inference method, which gives you the free energy estimate for free as your optimization objective, and you can just basically just publish that. And alternative, you can do sampling-based methods, whatever method makes you happy, and then estimate a free energy afterwards. And we want to be pretty agnostic to this for a variety of reasons. Namely, variational methods can be biased, and they introduce a level of complexity to the modeling that is often hard to deal with in many cases. But at the same time, so we want to be agnostic, but at the same time, our implementation that we've been building, it does lean specifically on stochastic variational inference. We've been using a variety of different SVI methods, depending on sort of different methods for creating variational posteriors that, there are different methods that are more appropriate to different kinds of problems, continuous versus discrete spaces, and so on. And what is the argument supporting that LLMs?
Could I just tack on to that last part?
Please. Yeah, of course.
Yeah.
Please.
In your experience of looking at what's been done in this idea of very large Bayes nets, or however you want to frame the problem, like where has this been done at scale, and what did that look like? Like, because this sounds like a tough challenge engineering wise.
Can you be more specific about this, because of everything, a lot of what we're talking about hasn't.
Well, yeah, I mean, I'm trying to get a sense for this. How much of this is a research problem to decide if the engineering aspect is feasible, versus
Right.
how much of this is sort of has other dimensions which are perhaps more complicated.
So, well, one of the nice things about SVI is that once you have a model, and there's automated ways to generate a variational posterior, and then you can just basically run Atom on it, and it will spit out an answer. So in that sense, it's a solved problem. The actually hard problem is, does it compute the right answer? So there's a lot of the active research on variational inference right now is on figuring out methods of generating posteriors that will propose the right posterior, will generate biased answers, especially in the case of high dimensional and multimodal problems. So GFlow nets again have been proposed as a pretty strong candidate for that. But I would say that is an area of active research. I think it's pretty doable, but you're correct that this is something where it is an area of research. Yeah. Cool.
Thank you. Yep.
Oh, you're welcome. Yeah, and to tack on to that first question, what is the argument supporting that LLMs are good for modeling, and can you define what I mean by this? Yeah, I mean, so if I go back here to again, this is pretty let's call it pretty early literature, so to speak, but it's very easy to verify experimentally and to advance on. So we're very confident that it will achieve a high degree of maturity quickly. Basically, if you have a target language, a target ontology, a target anything, let's say a target sort of state space that you want to describe models in, extracting a model in the broad sense, meaning the generative world, the generative models, the encodings of observations, encodings of questions from natural language is actually a very straightforward thing to do using LLMs. And if you're asking about, sure, don't they also introduce hallucinations? Yes, but again, this is where like not having to rely entirely on automated generation, but having this mixture of I don't know how, but this slide got skipped. I think the link that I shared also gave access to control the presentation.
Yes, sorry about that. Yes.
I did not see that one coming. So ignore that link and share a more appropriate one in a few seconds. Yeah, so LLMs can do this grunt work of turning, translating from natural language or from equations into code, and then there's all sorts of process that you can throw on top of it to which is this third layer here in Gedeon and Segeri's paper about things that you want to do to the candidate model, which you can do before deployment or during deployment as part of some collaborative network, decentralized model evaluation process that then gives you some sense of how good that model is. And the definition of what I mean by good at modeling is at this stage it is sort of intentionally vague, because ultimately what the requirement that I'm trying to get at here is much more a functional requirement of, can we generate candidate models that are good enough to get started to bootstrap the network at a scale that doesn't make it impossible to that doesn't take forever to get to a relevant scale. And that is my candidate solution. Cool. Does that answer your question, David?
I think so. I think what I'm listening for is how much model specification is given to the LLM, how much models are hypotheses that are sort of vetted against other knowledge in the network. So I haven't fully pieced together what you're going for, but I think I'm getting a sense for it.
Well, I mean, so I wanna be I'm always wearing two hats here. One of like the particular approaches that my team has been pursuing, which has been changing. We've been evolving that over time quite a bit. Like just this is this example that I'm showing here is from about 1 year ago, and even from that interval evolved several times the approach. And that is a lot more like human in the loop. It's more of an interactive. You provide a document, a PDF. The current version is more or less you provide a PDF that describes a let's say an environmental model, and prompt the system to translate that into a candidate generative model. And basically the user is assumed to be a domain expert that refines that model, finds inconsistencies, and is the same person that is going to be encoding like the use of that model. That's the general idea. But my other hat is just like, let's call it network architect. I want to highlight that there are solutions of that vein, and there's way more solutions, way more variations on that approach than I or anybody else can test for myself. So my hope is that, and we're already seeing this happen, but we really hope that with the explosion of AI coder and modeler, AI coder systems that is happening, this type of stuff will be a lot more accessible, and so we're going to see an explosion of different types of approaches that are going to produce a lot of really good, high potential candidate models that we can then throw into the mix.
Thank you.
You're welcome. Cool. So Joost has his hand raised, and Orpheus has a question in the chat. So Joost, why don't you go first?
Yeah, thanks. Because then I have to leave for my own session.
Yeah.
So as you know, I've tried to understand this whole thing about free energy for quite some time. Read some things, and I'm still very confused about things. So, for example, on one slide you had in a footnote that it is actually variational free energy that you're heading at. Now, my understanding from some papers is that variational free energy is a measure of how good an approximate Bayesian inference is given a model. It's not a measure of how good the model is as a model of some real world. Is that incorrect? And if that's correct, then isn't that the wrong thing that because you seem to be able to be wanting to measure the quality of the model rather than the quality of some variational approximation to some Bayesian inference that you want to do with the model.
Right. So great question. You can look at it both ways, actually. And so if you look at VAE type stuff, it actually has a bit of both. You have a parameterized model. You can automatically you can also calculate maximize the elbow in that context with respect to the model parameters. So it actually also works in the other way around. Does that help?
Not really. So are you saying the thing that you have some kind of I mean, we can't go into details here, but you have some form, some definition of variational free energy or whatever you kind of want to call it, that actually measures the quality of the model as a model for predicting real world outcomes?
Well, yeah. So the idea is that if you aggregate, let's call it, if you like look at batches or just a running tally of your model's ability to generate inferences that reduce variation of free energy across all the across data that is representative of your context, then that is a good measure of your model's ability to explain, to predict the environment.
But where in this whole setup here does a variational distribution come into play in the first place? I only see models, but where's the variational part?
Well, so the variational part is it's kind of tucked away, but for a good reason. So the what we call the model in a variational inference setting is both the generative model, which prescribes the structural assumptions of your system, and this thing called the variational distribution, or sometimes the guide, which is basically just an auxiliary distribution that just encodes the simplifications that you're making to be able to compute.
So when you say model, you mean actually the combination of the two?
Exactly.
Oh, okay, that was not clear to me.
Exactly, and I mean I'm fudging a little bit.
If that's the case, then I mean, as far as I know, and I have worked in science in many different fields, I'm not sure I know even a single example of a model that has this, that is of that type.
Well, so right, so I was gonna say that I'm fudging a little bit because the trend because of exactly what you said, the trend in variational inference is to generate these variational posteriors automatically, which in general you in general, you can do. It's still a little bit finicky in practice in the packages that are available, but it's basically a technicality. So in the long run, what's going to happen is that you can basically treat the choice of variation of posterior as sort of like this entailment or like technical sub bullet in your model specification, more or less like optimization hyperparameters. Like are hyperparameters part of your model? Theoretically not, but in practice, yeah, because you can't really in many cases you can't really use a model correctly if you don't understand the
Okay, I have to run for my own session. Thank you.
Yeah. Thank you. I'll see you there. Cool. All right, so we're running out of time. I'll answer Orpheus's question, and then if there's more questions, we can follow up on Discord. You can email me and so on. So Orpheus is asking about when do we want guarantees of proper verification from the network when the models are distributed but require gatekeeping? What do you mean by that?
Yeah, essentially, it's in the idea of well, I'm just imagining the Gaia nodes to be distributed and serving for gatekeeping, meaning controlling for the deployment